Hello and welcome back to Lecture 6. This is part 2. In this particular part, we're actually going to be proving the lemma that you see up on the screen there to the left, which is the linear dependence lemma. And this is going to be kind of a very useful tool. And I want to spend a couple of seconds here explaining more fully what's going on before we dive into the proof. So what it's saying is I have a collection of vectors, and I'm assuming that they're linearly dependent. And what this lemma is saying is that when you look at these vectors, you can take V1, and you can look at the span of it. Then you can take V2, and you look at the span of it. Then you can look at V1, V2, V3, and look at the span of that. Because they're linearly dependent, at some point, you're going to reach the case that after you take the first j minus 1, you'll see the next vector already in the span. So it could be that you have your first vector span and V2 is not in the span of that. Okay, so you put V2 in. So you have V1, V2. Now V3 may or may not be in it. If it's in it, then you're done. If not, throw it into your spanning set and then look at V4. Because it's linearly dependent, eventually you will find a situation where the jth one is in the span of the previous ones. And what the second part is saying is once you find that VJ, you can chuck it from your list and it doesn't change the spanning set. So in some sets, that VJ, if it's linearly dependent, you don't need it when you're looking at the spanning set. So it's a kind of an important lemma that we use to kind of build spanning sets later on in the course. So the proof is going to actually take all of this part of the lecture, but I'll try to go through it as slowly as I can. Okay, so just to kind of start off here, just remember that because they're linearly dependent, we're given a non-trivial solution with not all the AI equals 0. So what we're going to do is just say, well, let's look at this list. And at some point, there's some non-zero guys in here and some 0 guys. But let J be the largest index such that it's not 0. So once you go past J, you're not going to see any more terms. They're all going to be 0. So what that means is you could take your non-trivial solution and you write it as A1 times the vector V1 up to AJ times the vector VJ, and you still have 0. And just remember that it just means that AJ plus 1 is 0, AJ plus 2 is 0, so we can kind of like chop off the end. Okay, so now we have this with AJ not equal to 0. So we can actually rearrange this equation. We can take all the terms on the left-hand side and move it to the right-hand side, but we're going to keep the VJ on the left-hand side here. Okay, so that's what I'm going to do over here. We can rearrange the last equation, and what we would get is we get negative A1 over AJ times V1 plus negative A2 over AJ times V2, and we go all the way up to negative AJ minus 1 over AJ times VJ minus 1. And notice that this is all okay because this AJ is not 0, so we can divide. And each of these terms here are just coefficients. So look, we've taken Vj and we've written it as a constant times V1, a constant times V2, all the way down to a constant times Vj minus 1. So what this means is that the vector Vj is inside of the span of V1 up to Vj minus 1, which is exactly what we wanted to prove. So that proves the first part of the linear dependence lemma. Let's look at the second part. Okay, and so the second part here, let's go back to the lemma, is basically saying once you find this Vj, you can chuck it out from your list and your spanning set is still the same. And so because these are two sets, we need to show that everything on the left-hand side is in the right-hand side and everything on the right-hand side is in the left-hand side. Okay, so let's do one direction. Well, one direction is easy. V1, V2 up to Vj minus 1 and Vj plus 1 up to Vm, they all live in the span of V1 through Vm because these guys is just a subset of these guys right here. So we actually get one direction fairly easy because we know then that the span of these vectors has to be inside of the spanning set of V1 through Vm. So one direction is clear. It's the reverse direction where we have to do a little bit more work. Okay, so what we're going to do now is we want to take an arbitrary vector on this side and show that I can write it as a linear combination of the vectors that are in this list. So I take a vector u, and the vector u is in v1 through vm, and so u can be written as b1 times v1, bj times vj up to bm times vm. Okay, so we're kind of highlighting the fact here, something about vj. If this was 0, then we would be done. But the problem is bj might not be 0, so somehow we have to get rid of this term. Let me go up, and let me just call this star here for a second. Okay. Notice that what star is telling us is it tells me how to write star, how to write vj in terms of v1 and vj minus 1. Right? So I can make this substitution. Okay. So by star can replace vj with an expression in v1 up to vj minus 1. Okay, and I will actually do it right here. Because this vj, which we calculated above, we can actually write it in terms of the v1 to the vj minus 1. So it's negative a1 over aj times v1 up to minus aj minus 1 over aj, vj minus 1. And then we just throw in all the other terms that we had to begin with, bm, vm. Okay, now we've it's been broken up a little bit, but notice that we've taken u and we've now written u in terms of v1, v2 up to vj minus 1, and then vj plus 1 up to vm. We've kind of made the vj disappear. So because of that, u now lives inside of the span of v1 up to vj minus 1, vj plus 1 up to vm. Right? So thus, we have that the span of v1 through vm lives inside of the span of v1 up to vj minus 1, vj plus 1 up to vm. And so going back up at the beginning, we showed this set was contained in the span of v1 through vm, but now we've just shown that the reverse inclusion also holds so that these two sets are the same. So to re-emphasize here, what we're doing here is when you have some linearly independent, at some point, when you look at them kind of one at a time, at some point you will find a VJ that is a linear combination of the things that you've seen before. And when you ever find that guy, you can remove it from your list and you still generate, or you still have the same spanning set from the same set of vectors. Okay, so we'll pause here. This was a complicated proof, and we have another kind of more complicated or more involved statement as well. And again, I'll explain it in more detail.